Let's see, let's pick it up. Number 1. Which of the following general reaction types is characterized by there being a single reactant? If you have a single reactant, the only thing it can do is decompose, right? Yeah. So decomposition is the only possibility. Well, that was simple. Moving on. 4. Proper assignment of oxidation numbers to the elements in the polyatomic SO3 2-. All right. SO3 2-. Remember the rules. Oxygen is always -2 except in peroxides. That's not a peroxide. So it's -2 for each one of those oxygens, -6 total oxidation number for this oxygen. But we need to add them up so we get 2 minuses left over. That means we only need to neutralize 4 of those. That means this has to be a +4. So a +4 and a -2 would be D. All right. Six. Which element is oxidized in the following redox reaction? So we have 2 hydrogen sulfides plus an oxygen yields 2 waters plus a sulfur. Okay, which one is oxidized? Remember how to tell oxidation? Oxidation is loss. Reduction is gain. So we need to do, the easiest ones to do first are the elements. They're always 0. Okay. -2 for that oxygen, +1 for the hydrogen. And hydrogen is going to be a +1. That means this has to be a -2 to balance. Okay. So if we go, hydrogen didn't change. Oxygen did change. But what happened to it? It went more negative. That means it was reduced. So this is the reduction. That means this sulfur going from here to here is the oxidation. It actually lost 2 electrons for each sulfur. Okay, so let's see. Sulfur in hydrogen sulfide was oxidized. All right. Number 7. Which substance functions as a reducing agent in the following redox reaction? All right, so we got methane, 2 oxygens, yields carbon dioxide and water. Okay. What type of reaction is that? Well, obviously a redox reaction, right? Because oxygen is elemental here and it's in compounds over here. But it's also a combustion. Anything combined with elemental oxygen is a combustion. So it's both of them. Question is reducing agent. So the reducing agent is the one that's oxidized. So again, this one's 0. This one's -2. This one's -2. That means this one's +4. And of course, this one's +1. Let's see. Yeah, this one's +1. That means this one's -4. So the carbon went from -4 to +4, which means it was oxidized, right? Okay. I think we found our culprit. Oxidized. How many electrons were actually lost in this process? I try to go to 0, and then if I need to, I'll go beyond. So -4 to 0 would be a loss of 4, right? 0 to +4 would be a loss of another 4. So actually there were 8 electrons lost for each carbon. Okay. And the reducing agent is always the oxidized. So we found our methane is the reducing agent. All right. Number 8. I think this is a little more work using a microfiber, but this other thing just smears it around. Number 8. What's the change in oxidation number for cobalt in the redox reaction? All right. Here's illustrates a point. 2 CH203, right? Plus 3 elemental carbon yields 4 cobalt plus 3 CO2. This illustrates the point that you got to watch yourself with capitals and smalls, right? C little o is cobalt, C big O is carbon dioxide or carbon monoxide, depending on how many oxygens. Okay, so back to the question. What's the change in oxidation number for cobalt? Okay, so if we have a -2 here, that's a -6 total. That means +6 for both of them, +3 for each one. And then the cobalt here is 0. So it gained, going from here to here, gain 3 electrons for each cobalt. Okay, it's just asking us the difference in oxidation numbers. So it went from a +3 to a 0. That's D. All right, number 12. The minimum combined kinetic energy reactant particles must possess in order for their collision to result in a reaction is called what? The minimum kinetic energy. This is definition. That's called the activation energy. Sometimes we write it like this. Activation energy. While we're here with this collision theory, what are the 3 required components or postulates for the collision theory to explain a reaction? One is you have to have a collision, right? Those reactants must collide with each other. Except that brings up a question. What about the reactions where there's only one particle? I mean, where there's only one reactant? Decomposition? How do we explain that with collision? Well, it doesn't have to react with the other particles, but it must slam into its neighbors with enough energy to break bonds. And they don't necessarily react with each other. It's just enough to get the decomposition started. But if there are 2 or more reactants, then they have to collide. Okay, then we need the minimum energy, right? And the third one. What's the third one? What if they collide with enough energy, but their reaction sites are on the opposite sides of the molecules? Right? When they collide, nothing happens. They have to be oriented correctly. In order for the reaction to proceed. Those are the 3 postulates for the collision theory of reactions. All right, 13. Whether a reaction is exothermic or endothermic is determined by. All right, if we look at the progress of a reaction going this way, and the energy of all its components. If its components start out at, say, this energy where we have reactants, and then we need a minimum amount of energy, right, to get over the top, right? Between here and here is the activation energy, right? And then we have products. Okay. What's the relationship here that tells us whether it's exothermic or endothermic? It's the initial energy versus the final energy here. That's the enthalpy of the reaction. Okay, now to answer that question. Compare the potential energies of the reactants and the products. That's all that's required. The energy contained in the reactants versus the energy contained in the products. And remember, conservation of energy is observed. So if it goes in with a certain amount of energy and comes out with this amount, the rest of it has to go off as something else. It could be heat. It could be light. What else? Forms of energy. Those are the two biggies. All right, so C is the answer for this one. All right, 14. Stay put. Okay. Which of the following changes is most likely to decrease reaction rate for the chemical reaction? So if we have 2 carbon monoxide plus oxygen yields 2 carbon dioxide, what affects the reaction rate? These are all gases, right? It doesn't say gases, but we know they're gases. Carbon dioxide, carbon monoxide, they're all gases. Oxygen's a gas. All right, so we can't say anything about particle size, right? Because they're all gases. So let's look at each one. Adding twice as much oxygen to the reaction mixture, is that going to speed it up? No. If it reaches equilibrium and then we add some oxygen, it'll speed up temporarily until it reaches equilibrium again. But we're talking about overall reaction. So A is not a good answer. Triple the temperature of the reaction mixture. Well, we can't say anything. We cannot deduce anything from the reaction as given about the reaction rate. We might be able to say something about equilibrium. Remember, rate and equilibrium are two concepts. And that diagram I showed you earlier, the energy diagram, the tails on either side, right? That's equilibrium. This is kinetics. Right? So the way to speed the reaction up is somehow get this value, this activation energy, lower. So adding a catalyst to the reaction mixture. Decrease the reaction rate, excuse me. If we add a catalyst, we're going to speed it up, right? So remove some CO from the reaction mixture. Okay, the reaction rate will increase if we we can increase the rate by increasing the number of collisions. Let's look at it that way. If we increase the amount of oxygen, that's A, then that will actually speed the rate up until it reaches equilibrium. If we remove one of these reactants, then that reduces the frequency of collision, which will reduce the reaction rate, at least until it reaches equilibrium. All right, but when you first put them together, the concentration of each one, if you increase the concentration of one or the other or both, then you increase the rate. Decrease it, then you will decrease the rate. So removing some carbon monoxide from the reaction mixture will decrease the rate. Did I confuse you? Just a little bit. I kind of danced around it for a while before I settled on an answer. It goes back to the collision theory, right? The more frequent the collisions, the higher the rate. The less frequent the collisions, the lower the rate. That's a simpler explanation. 15. This is a question about catalysts. They're correctly characterized by each of the following statements, except for one. Okay? They can be either solid, liquids, or gases. A? Yep, that's true. Catalysts can be any one of these, solids, liquid, or gas. B, they lower the activation energy of the reaction. That is true. They do not actively participate in the reaction. That's false. They do actively participate in the reaction. It's just that they go in one end and come out the other. And from a macroscopic observation, it looks like they didn't do anything because they go in here and they come out here. You know, what happened in between. That's mechanisms. And we don't get into that in this course. They're not consumed in a reaction. That's true. Yep. They are not consumed. Okay, so we found our answer. Number 17. Do a little math here. Equilibrium expression. Okay, so if we have 4HCl, hydrogen chloride, because it's a gas, we name it that way. In aqueous solution, it would be hydrochloric acid. But as a gas, it's hydrogen chloride. O2 gas is in equilibrium with water vapor, actually. These are all gases and 2 chlorines. Okay. So when we write the equilibrium expression for this one, which ones can we include in the expression? All of them. But if they're gases or in solution, their concentrations do change during the reaction. If they're pure liquids or solids, their concentrations do not change. So they're left out. But we include all of these. So that means in the numerator, we're going to have water squared and chlorine gas squared. And in the denominator, we have hydrogen chloride to the 4th power and oxygen to the 1st power. So let's see which one of those satisfies. C, looks like C works. Yep. That would be the equilibrium expression for this equation. Okay, Le Chatelier's principle. That's the one we were going to do today until I canceled it. Number 18. Let's see. What does it say? Le Chatelier's principle simply says that a reaction at equilibrium, that's your starting point. A reaction at equilibrium if stressed. We have to define what we mean by stressed. if stressed, will respond to reduce the stress, the effects of the stress. Now see which one of these matches that one. C looks pretty good. If a chemical equilibrium is disturbed, the system will try and reestablish equilibrium. Yep. So how do we get there? What are the types of stress that an equilibrium system can experience? Change concentration of reactant or product. That could be addition or subtraction, removal or addition, and that will stress the system. How about change temperature? Right? This one's easy to work with. How about what does change temperature do? Well, there's a rule of thumb and then there's the actual chemistry. The actual chemistry, change temperature means you change the K value itself. And it depends on whether the reaction is endothermic or exothermic. So the rule of thumb is if you write the reaction and it's exothermic, then the heat term goes on the right because it's releasing. If it's endothermic, then the heat term goes on the left. And that way, if the heat term is on one side or the other, then you change the temperature, you change the heat term, and you read the reaction response as if it were a change in concentration. That's the easiest way to deal with it. And then what's the third one? Pressure. Change pressure. Now, what would happen if, say, we had a gas reaction like I wrote up there before, just in the past, in 17, and we altered the partial pressure of one of the reactants or products? Does it always change the equilibrium position? Not necessarily. It only changes the position if the number of moles of gas on the reactant side is different than the product side. What if I introduced an inert gas into the system and increased the pressure that way? No effect, because the inert gas doesn't participate in the reaction. The change in pressure references a change in partial pressure for a reactant or product. Okay. All right. Okay, that was 18. 19. Carbon dioxide and hydrogen are allowed to react until an equilibrium established as follows. Okay, carbon dioxide, hydrogen yields water and carbon monoxide. Water, carbon monoxide. And these are all gases. Yep, they're all gases. All right. Okay, we're at equilibrium. What will be the effect on equilibrium of removing carbon monoxide from the equilibrium? So we remove carbon monoxide after equilibrium. The effect will be to shift the reaction as written to the right, toward products. So let's see. Hydrogen concentration will decrease. Yes, if we move this way, that will decrease. And water concentration will increase. Yes. We don't change the equilibrium constant. we change the equilibrium position. Those are two related but different concepts. Because the position can be any concentration at all. The constant is constant for a given temperature. All right. Oh, there's our Haber equation. According to Le Chatelier's principle, which of the following changes will shift the position of the equilibrium to the left for this reaction? All right, so Fritz Haber got nitrogen and combined it with hydrogen. Yep. 3 hydrogens in equilibrium with ammonia. So 3 and a 2. Oh, and it's exothermic. That says heat. I always write delta H. So shift the position to the left. Well, there are several ways you can do that. You can remove one of these. You can add some of this, or you can increase the temperature, right? To the left, yes. We're moving to the left, increase the temperature. Of course, if you want to make ammonia, that's not a good way to go. So A says double the concentration. Nope. Decrease ammonia. Nope. Increase hydrogen. Nope. Triple the temperature. Oh, yeah. Increase the temperature. You go that way. Now, according to the collision theory, the higher the temperature, the more of the reactants reach or above the activation energy, which is what you need. And then you increase the pressure, partial pressures of the reactants, you increase the frequency of collision. So that's a good thing. And that's what Haber did originally. But the problem there is he also recognized that the reaction is exothermic, and increasing the temperature is going to drive the reaction this way. So how did he get around that one? He did 2 things. Added a catalyst, which makes the reaction go faster. It doesn't change the equilibrium, but it makes it happen faster. And the other thing he did was he cycled. He cycled the reactants and products. These are all in the reaction vessel together. So he bled off part of it and sent it through a low temperature loop. And the low temperature loop removed ammonia. And then he sent the nitrogen and hydrogen, which stayed as gases at the temperature he chose, because the boiling points here are much, much lower than ammonia. So at this temperature, ammonia came off and he sent these back in here. So he removed product and he drove the reaction this way. It wasn't a huge advantage, but if you cycle it 4 or 5 times, then you start to get industrially significant efficiency. And that was Haber, and then Bosch came along and modified the engineering of the reaction and produced something that could be used industrially. And that's why Germany was able to produce their own munitions during World War I. Okay, 22. In which of the following compounds does chlorine have an oxidation number of +5? Okay. B, C. How many do we have? D? E. No. Yeah, E. So more than one or none? So we have hydrogen hypochlorite, potassium chlorite, and calcium chlorate. Okay. Now we could do this thing just, take all neutrals and just work it out. But if we're looking for chlorine, I say these are polyatomic ions. That one is ClO. This one's ClO2. And this one's ClO3. Okay. So each one of these oxygens is a -2. That's a -2 here, -4 there, and a -6 there. But each one has to have a negative left out. So we only have to balance that one, -4, -3, and -5. That means this one's +5. Okay. That's the quickest way to get there. That would be, wait a minute. ClO2. That's the wrong answer, isn't it? Should be C. Let's check it the old way and see. -2 +1, which is -1, that's +1. Yep. Okay. -4 total here, +1 there, -3 is a +3. Yeah. So this would be +5, +3, +1 for the chlorines. And this would be -2, which would be -6, -12. Right? Because there are two of them. And this is +2. So that's +2 and a -12 is -10, but we have two chlorines, so each one has to balance a -5, +5, +5. Yeah, that answer is wrong. It should be C. I'm gonna change it right now. What was that? 22. Yeah, that one got past me. Should be C. I need to change that in the computer too. Not just this one, but the one I hand out. That is, now I'm working from a key. Did I already change it in this one? 22.
It's C on the interview.
Oh, okay, so your answer key is C.
Yeah.
Okay, good. So I already changed it there, I just didn't change it in my key. Okay. It's changed now. All right. '23. In which of the following sequences of sulfur-containing ions are the ions arranged in order of decreasing oxidation number for sulfur? All right. Oh, how are we going to do this one? All right, decreasing oxidation number. So they could go from very positives to not so positive, or to 0, or they could go to negative, or they could go from 0 to negative, or they could go from negative to more negative to decrease the oxidation number. In other words, more negative is decreasing. Whether it starts off positive or starts off negative, doesn't matter. All right, so let's see. see. And this is SO3 and SO4. SO3, SO4, and S. Okay. And SO4, we'll already have that one done here. S203, 2 minus. S203, 2 minus. That's thiosulfate. Yeah, thiosulfate. And then this one will already be done. And then the last one, that one, we'll already have that one done there. And we'll already have this one done. And we'll already have this one done. So it's not as bad as I thought. First one. So if this is a -2, then it's a -6, and we only have to balance -4 because we need to keep 2 of these out for that charge. So this is a +4. If this is -2, -8, keep 2 of those out, -6, this is +6. And this is a 2 minus. Okay, so there's a 2 minus. This is a +6, right from there. This one, 3 times 2 minus is -6, but we need only -4. So this would be a +4 total, would be a +2 for that one. And +2 here. In SO3, this is +4. And this is +6. So we're looking for a decrease in oxidation number. This increases oxidation number, so that's not it. +6, +2, 2 minus. That's a good one right there. Because this one increases and then decreases, so that was not it. So B should be the right answer. Okay. 24. Which of the following reactions is non-redox? Okay. Let's see. Calcium carbonate is heated in a furnace and makes lime. Right? That's how they make cement, concrete cement. They just take calcium carbonate, grind it up real fine, run it through a hot furnace. It blows off the CO2 and leaves you with calcium oxide. Then you mix it in to make Portland cement. All right. This is a -2, -4, +4. This is, let's see, -2, +2. This is +2. This is -2, -6. So that's a -4, +4. That's not redox. Oh, which of the following is non-redox? Oh, sorry. We're looking for the non-redox, right? So that's one of them. How about this one? Well, potassium chlorate will decompose into potassium chloride plus oxygen. 3 of them. All right. That's the stuff we just put on the floor as a liquid. When it dries, then it becomes shock sensitive. And when your lab assistant or your professor walks through and steps on it, it'll go pow under their foot because it produces this gas. It's not dangerous. It's just funny. All right. This one is, you can use your rule of thumb or your trick. That's an element. That's in a compound. This is a redox. So it doesn't fit the bill. How about SO3 plus H2O yields synthesis reaction. SO4. Yep. Okay. -2 + 1 -2 is a -6 total, needs a +6. This is a -2, so that's a -8 total. This is +2. -6 there, so this has to be a +6. Right. So this one is a non-redox. So A and C, more than one correct answer. Okay. My guess is that lab assistants that have been around for a while and professors that have been around for a while are going to suspect that's a possibility. So they're on the lookout for these little white spots on the floor. So you have to start with a newbie. All right. 25. I think you remember those. Well, it's probably been, you're too young to remember. They used to have these little things that looked like what do they call those cereals with the round crunchy pieces in them? Tricks. They used to make I don't know what you call it, kids' toys with those little things, and all you have to do is throw them on the ground and they pow. I think they had potassium chlorate in there. And then when they hit the ground, they would.
Like little poppers, like little tiny bags.
Yeah, they still make them.
I think like, there's a grocery store of Little Creek.
Uh-huh.
They still sell
Okay.
those.
I think that's what they have in them. And all you need is that shock and then they'll explode. 25. Which of the following statements concerning oxidation reduction is correct? All right. Let's see. More than one correct response, no correct. So we got to look at the A, B, and C. A, B, and C to be sure. All right. Is A correct? They cannot occur independently of each other. Yeah, oh, that's true. That's why we call them redox, because with the reduction, you always have an oxidation. B, they accompany all chemical reactions. Nope. Not necessarily. And C, they describe respectively the gain and loss of electrons. Oxidation reduction. Oxidation is loss. Gain is reduction. That's reversed. So that one's false. So A is your only answer. 26. In the redox reaction, iron plus oxygen plus hydrogen chloride yields iron 3 chloride plus water. Okay. A through C. And let's see. We better write this one out. Plus 3 oxygen plus HCl, 12 of those yields 4 of these plus 6 of these. All right. So let's see. Oxidation states 0 there, 0 here, -1 plus 1, -1 plus 3. We have to assume chlorine is -1 here. Otherwise, we can't tell what iron is. -2 and +1. Okay, what changed? Iron changed. Iron is oxidized. Okay. Oxygen went from a 0 to a -2. It's reduced. Okay, that's a good starting point. Let's see what the questions are. HCl is a reducing agent. HCl doesn't do anything. -1, -1, +1, +1. So A is false. because hydrogen chloride doesn't do anything. Oxygen is a substance oxidized. No, it's the substance reduced. Right, so that one's false. How about C? Iron undergoes an oxidation number decrease. Oxidation number, yes. So, no, it increases. It's oxidized. So it's gain of, no. Duh. Oxidation is loss. Loss, 3 electrons per iron. And that means the oxidation number increases. So iron undergoes an oxidation number decrease? No, it's an increase. Okay. We have to pay attention to the wording. So no correct answer. All right, they're all false. Let's see, 27. In the redox reaction, the oxidizing agent is the substance reduced. So it gains electrons or it's reduced. A, oxidized, nope. B, that loses electrons, no. Oxidizing agent gains electrons. It causes oxidation. So it has to gain those electrons from something else to oxidize it. All right, so B is also false. C, that contains an element that undergoes a decrease in oxidation number. Yes, if it causes the oxidation, it has to be reduced. So its oxidation number must decrease. It has to add electrons. It has to add those negatives. That's the same idea as decrease. So C is the correct answer. 28. For a collision between molecules to result in a reaction, the molecules must possess a certain minimum. Wait a minute, we did that one already, didn't we? Certain minimum energy. And. Okay. Exchange electrons? No, not necessarily. Interact with a catalyst? No. Catalyst doesn't have to be there. Have a favorable orientation relative to each other. That's a good one. See? Well, those are only 3 choices. So C is a good answer. Yep. All right. 31. Chemical equilibrium is reached in a system when? Chemical equilibrium implies forward rate equals reverse rate. That's why in my general chemistry class, let's see, this coming semester, we don't do it the first semester, the second semester, we study kinetics first, reaction rates first, because the equilibrium depends upon that fact. So we learn about rates, then we learn about equilibrium. That's not historically the way it happened, but it's a better way to understand it. So which one says that? Reactants are being consumed at the same rate they are being produced. C is a good answer. Yep. (34) According to Le Chatelier's principle, which of the following effects will occur if ammonia is removed from an equilibrium mixture governed by this equation? Now, we talked about that earlier. If you remove ammonia, it's going to shift the reaction as written to the right. So that means we're going to decrease nitrogen, decrease hydrogen, shift the reaction to the right, or increase the heat. So A says concentration of N2 will increase. No, it'll decrease. Heat will be generated. Yes. Yeah. So B is correct. And C, concentration of H2 will decrease. C is also correct. All right, so we have more than one correct response for the Haber equation. $35. For which of the following equilibrium systems will the equilibrium position shift to the left when a stress of increased pressure from a volume decrease is applied? So our mixture is in there, it's an equilibrium, and we squeeze it. We increase the pressure, the partial pressure of everything in the reaction mixture. So which way will it shift? It will try to reduce the number of moles of gas when we increase the pressure. So we need to compare A, B, and C for reactant moles versus product moles. So for A, we have 9 reactant moles of gas, and we have 6 product moles. So we want to shift the equation to the left as written. That will go to the right with an increase in pressure. So that's not it. How about B? We have 2 moles of gas here, and product we have 2 moles. Nothing happens. You got the same number of moles gas on both sides. You can change pressure all day long and nothing will happen. In terms of the equilibrium. Let's see, the last one, H2Cl2, that's 2 moles, and the product is 2 moles. There's no correct response. None of them will shift to the left. Now, what if we wrote this reaction in reverse? Then it would do it, right? But as written, no, doesn't work. That's why it's important when you say shifts left or right, you're referencing a balanced equation. All right. Oh, one of these. All right. 39. What are we doing? We've only been at it an hour. So let's see. We got to look, see which ones of these are true. Number 1, the only information needed to write an equilibrium constant expression is a balanced chemical equation with physical state information for the reaction of the concern. Oh yeah, that's all you need to write the expression. You need to know the states so that you know which ones to exclude, if any, solids and pure liquids. How about 2? The oxidation number of sulfur is the same in the species H2SO4 and SO4 2-. That's true also. The reason I know that is H2SO4 has SO4 2- in its makeup. So you're essentially calculating the oxidation number for sulfur for the same molecule. It's a polyatomic ion. Right? So how about 3? Increasing the concentration of a reactant makes collisions between the reactant and other reactants less likely because of more crowded. No, it makes it more likely, right? So 3, it's false. So we only have 2 that are correct. That would be B. Okay. All right, let's see. We'll skip a few of those. There's another one, 45. Now we can stop at any one of them. If one of them gave you trouble or interested you, then we can do any one. It doesn't have to be highlighted. These are just ones I picked out because I thought they were unique and teach worthy. 1, 2, and 3. All right, 45. Of the known atmospheric greenhouse gases, CO2 is both the most abundant, also the most efficient in preventing heat loss from the earth. That is patently false. What's an example of a gas that's more efficient than CO2? Methane. Methane's a lot more efficient at trapping gases. Which one is more abundant than CO2? Water vapor. It's less efficient, but there's orders of magnitude more of water vapor in the atmosphere than there is CO2. So CO2 as the culprit for global warming is a pipe dream. How about 2? Ozone is a form of oxygen in which there are 3 atoms per molecule. Yep. That's ozone. So that's 3. A decrease in body temperature slows down the rate of chemical reactions. Yes, it does. Right. So 2 of the above are correct. And then what's the rule of thumb for chemical reaction rates? Did I give you that in class? For every, let's say increase. Say for every increase of 10 degrees C, rate doubles. And that's a generalized. It varies quite a bit, but that's a good place, a starting point. And the same thing goes for decrease. You can decrease the reaction rate by lowering the temperature by 10 degrees. So that's why if you want to preserve something from chemical degradation, just dunk it in liquid nitrogen. Minus 195 degrees C compared to room temperature is like, let's say, minus 200 roughly plus 20. That's 220 degrees. So 220 divided by 10 is 22. Oh, no, it's compounded. It's compounded. It's reaction rate to the 22nd power. So you're decreasing the reaction rate down to almost nothing at minus 195. So that's why they take cell cultures and dunk them in liquid nitrogen. They preserve them as long as forever. And the quicker you can freeze something, the more likely the cells are to remain intact. When you freeze slowly, the ice crystals grow slowly and big. And if they get bigger than the cell, they'll punch holes in it. So then when you thaw it out, all that stuff comes oozing out of the cells and it's a mess. So when you freeze something really fast, the crystals are extremely small and they're smaller than the cell itself, so they don't rupture the membrane. So when we used to freeze dry stuff for preservation and later chemical analysis, we would take plant samples and dunk them in liquid nitrogen, and then we would freeze dry them. So that way you can remove the oxygen by sublimation, the water by sublimation, and leave the cells intact. Okay, 46. That's why these, what do they call them? Survival packs? Foods that you can buy that are ready to eat, and they're sealed in metal lined containers. You just pop them open and add water. They've been freeze dried. They were frozen quickly and then freeze dried. So they're good for 20, 25 years. That's advertised a lot on the radio now. These survival packs, 3 months worth of food for one person. For my family, it'd only be 1 month. There are 3 of us. Assign the following reaction to one of the reaction classifications given in the response list. Okay, so what do we have here? We've got Two reactants making one product. That's a synthesis. Or let's see, a combination. Their term is combination. Either way is a correct description. 49. Assign the following reaction to one of, oh, okay. Oh, so we've got potassium cyanide, right? That's every murderer's good friend. And then hydrogen cyanide plus ACl. Oh. Okay. Here's how you execute a prisoner. Yeah, potassium cyanide in the bucket underneath his chair. He's strapped into it in an enclosed, hermetically sealed chamber. Then you have under there hydrochloric acid in a little vial. And then you either break it or you drip it into the potassium cyanide. It produces hydrogen cyanide gas that wafts up through the air. The prisoner breathes it in and croaks them. All right, let's get back to the question. What type of reaction is this? Well, when you have two binary compounds, right, this is a polyatomic ion, right? And it's the same on both sides. So you got this part and these two parts, you just trade places here. So the potassium combines with the chlorine and the hydrogen combines with the cyanide. That's a double displacement. Or, well, they call it an exchange reaction. Okay. They're calling a displacement what I call a single displacement or single replacement. But an exchange reaction is a double displacement. So D is the correct answer for this one. I don't know how many states still use that one. I think some of them have a choice. You know, if you're a condemned prisoner, you can choose. I think one state I heard it was you get lethal injection, firing squad, or hanging. They didn't even make this one available. Let's see. We've also got electrocution possible, right? So you got electrocution. Yeah, the chair. Well, yeah, electric chair versus gas chair. And then firing squad, and then lethal injection or hanging. So you got 5 choices, basically, depending on what state you're in. Now, Georgia has the death penalty. That guy that killed Lake and Riley, they should put him out of our misery instead of paying for his room and board for the next 60 years. They ought to get rid of him right away. That's my opinion. 52. For the indicated element, select the correct oxidation number from the response list. Sulfur and H2SO4. All right, this is fairly simple. We have 2 choices. We can use the polyatomic ion or the whole molecule. Oxygen's -2, so that's -8 total. Hydrogen's +1, so that's +2. So together they have -6. That means 1 sulfur has to be +6 to balance it. So that would be D. 53. I can leave that one up there and just do this. What's carbon in potassium hydrogen carbonate? Potassium hydrogen carbonate. And we're looking for carbon. Okay. So this is -2, -6 total. That's +1. And that's +1 because it's an alkali metal. So together, that is -4, correct? That's +4. Okay. Consider the following redox equation, 56. So the question tells you it's redox. SO2, NO2. 6. SO2, NO2. And SO3 plus NO. Yeah. There we go. We identify the oxidizing agent. So the oxidizing agent is the one that's reduced. All right. So that's -2, -4. This is +4. -2, -4, +4. Yeah. This is -6. This is +6. This is -2. That's +2. Okay. So which one, oxidizing it, which one is reduced? +4 to +6. That's oxidized. Oxygen doesn't change. Nitrogen went from +4 to +2. That's the one that's reduced. So this is our reducing agent right here, NO2. Okay. Let's see, 62. For the following general reaction, choose the correct form of equilibrium constant expression. All right. So we have 2x gas plus 3y solid is in equilibrium with 2z gas. Right? So the equilibrium expression excludes that one. That means we have z to the second power and x. Oops, did I write that right? Yeah, 2 and 2. X to the second power. We could write this as, I don't know if we're going to need it, but we could write it this way, and bring the power outside. That would work. No, we don't need it. B works. Right. There's B. I'm just exercising my algebra brain. Right. 62. 64. Determine the effect on the position of equilibrium when some CO2 is removed. So if it's at equilibrium, for this equation, carbon dioxide plus hydrogen yields methane plus water. CO2 is removed. CO2 is a reactant. So if we remove some of it, the shift is going to be to the left, correct? As written. Yep. Okay, that was simple enough. Oh, same equation. 66. What's the effect on equilibrium if you add a catalyst? Does not. Nothing happens to it. Equilibrium does not shift. It just gets there quicker if it's not at equilibrium. 67, same equation. Volume of the container is increased, pressure is decreased. So what does that mean? That means if we decrease the pressure or increase the volume, the system is going to try to make more gas to fill the space. As you create more space, it's going to want to fill that space. So we have 4 moles on the left in equilibrium with 2 moles on the right. So if we increase the volume, it's going to move to the left. See, I don't have this one highlighted, but what about if we decrease the temperature? The heat term is on the left. If we remove that, some of that heat, the equilibrium should shift to the left, right? So that's also B. Oh, now we're getting into acids and bases. Okay. This must be chapter 10. Oh, we're starting our numbering over again. Ooh. I should have written what chapter we were in. Okay, we're starting over with numbering. Okay, chapter 10, 3. This reaction, N3 minus, which is the azide ion, plus H2O, yields HN3 hydrogen azide plus OH minus. Okay, Bronsted-Lowry base. Bronsted-Lowry acid donates protons, base accepts protons. So which one accepts the proton? It accepts a proton from here to make that. So this is the conjugate acid. Right? Water serves as an acid and makes a conjugate base. Okay. Oh, so the answer is N3 minus, A. Let's see, 4. Which of the following is not a conjugate acid-base pair? All right, A, B, C, D. So remember what is required for a conjugate acid-base pair. You have to have the same core, and the two differ by 1 proton. So acid-base means this is the acid, that's the base, has 1 extra proton here, loses that proton, makes the conjugate base. That's an acid-base pair. That one is good. Oh, not a conjugate acid-base pair. I got to read my own question. All right. This is an acid-base pair, which means it doesn't fit the conditions. How about this one? OH minus and O2 minus. OH minus and O2 minus. Oh, excuse me. O2 minus. There we go. When it loses that hydrogen, the hydrogen leaves an electron behind and makes the proton. So yeah, it gives you a 2 minus charge. Okay. That one is an acid-base pair also. How about C? H3PO4 and H2PO4 minus. Yeah, that's an acid-base pair. This proton, the positive leaves, an electron stays behind. That's where this charge is. So that one's good also. So by process of elimination, D should not be an acid-base pair. CO2 and CO3 minus. Well, obviously, there's no proton there. Plus, the difference between the two is not hydrogen, it's oxygen. Right? So that one's the wrong one for number 4. Okay, 5. Which of the following pairs of acids are both members of the pair strong acids? All right, we got A through D. A, B, C, and D. Both of them are strong acids. How about A? Sulfuric acid is strong, but phosphoric acid is not. So that's false. Let's see. HI and HNO3. Yeah. Right. HCl, HBr, HI, all of those halogens make strong acids. The one that's weak is that one. These are strong. Okay. So, yeah, both of them. That's true. Well, we found our answer because we don't have any wonky ones in there. H2CO3 is carbonic acid. It's weak. HI is strong. And D, HC2H3O2, which is acetic acid, vinegar. That's a weak acid. HI is strong. So the correct answer is B. Both of them are strong. And number 6, let's scroll a little bit here. In which of the following pairs of acids are both members of the pair polyprotic? Polyprotic means 2 or more hydrogens available for dissociation or ionization, right? So that means you have to have 2 at the very beginning of the molecule. All the other hydrogens in the other parts of the molecule are not available. So A, sulfuric acid is polyprotic. Acetic acid is not. Nitric acid is monoprotic. So it doesn't matter what the other one is. C, same thing. Acetic acid is monoprotic. And D, H3PO4 and H2C4H4O7. I'm not sure what that is. Both of those are polyprotic. Right? D is the one. We're just focused on those hydrogens so we don't have to know what the rest of the molecule is. 7. Which of the following is produced in the first step of the dissociation of the acid H3PO4? All right. Polyprotics dissociate, and I'm going to use the simplified version rather than the true. So what it gives us is that and that. Okay. Let's see. B. Yeah. Oops. All right. Only one proton at a time. So that would be B. Let's see. 11, 12, and 13. A solution with a pH of 13.3. pH of 13.3. Is that acidic or basic or neutral? Not neutral. pH 7 is neutral. High pH is basic. Greater than 7. And it's strongly basic, actually. That's a very high pH number. So D would be the correct answer for that one. Strongly basic. 12. Which of the following does not describe an acidic solution? Ooh, okay. A, B, C, and D. All right, the first one is pH is less than 7. That's an acidic solution. pH less than 7 is acidic. We're looking for the one that doesn't describe an acidic solution. OH minus, equilibrium concentration, is greater than 1 times 10 to the minus 7. If it's greater than that value, it's basic. Right. So B is a good answer. C and D should be acidic. H3O, the hydronium ion is greater than the hydroxyls. Yes. If this one is greater than this one, that's acidic. And D, OH minus is equal to 6 times 10 to the minus 10. That's a lot less than 10 to the minus 7. So this ion is less than that one. Remember, hydrogen ion concentration times hydroxyls at 24 degrees C is always equal to 10 to the minus 14. So 10 to the minus 7, 10 to the minus 7. If this is much, much less than 10 to the minus 7, that means this one is much greater than 10 to the minus 7. That's acidic. Okay. All right. That was 12. Thirteen. If the pH of a solution increases from 3.1 to 5.1, so pH from 3.1 to 5.1, the hydronium ion concentration, what? If the pH goes from this number to this number, remember it works backwards. So what factor has it decreased the hydronium ion concentration? Remember, pH is a logarithmic scale. So if it goes from 3.1 to 4.1 is 10 times. 4.1 to 5.1 is another 10 times. That's 100 times. But it's going the opposite direction. It's actually 100 times smaller. Decrease by a factor of 100. That would be D. Number 14. All right. In which of the following pairs of salts would both members of the pair hydrolyze in water to give solutions that are basic? All right. Rule of thumb. If the salt is formed from the reaction of a weak acid and a strong base, you get a basic solution. So we look at how theoretically the salts could form. Lithium chloride. Lithium is an alkali metal. Lithium hydroxide is a strong base. Hydrochloric acid is strong acid. This is neutral. We want a basic solution, so it doesn't matter what the other one is. Like sodium cyanide, that one would be basic. Because this would form from sodium hydroxide and cyanic acid. Cyanic acid's weak. Strong base, that gives you basic. Ammonium chloride. Strong acid, weak base. This is acidic. And NH4, NH4NO3. Nitric acid and ammonium hydroxide. This is weak base, strong acid. That's acidic. Okay, how about C? This is from, oops, sorry. C. C2H3O2. The acetic acid is weak, and this is strong, so it's a strong base. It's basic. And the second one, sodium fluoride, this is from a weak acid. That's a strong base, so this one's basic. Okay, both of those are basic. I think that's the answer we're looking for. KNO3, potassium hydroxide versus nitric acid. They're both strong, which makes neutral. And then lithium hydroxide is strong. Sulfuric acid strong. So we got neutral for this one. So here's our answer there. C. Just using the rule of thumb. Now we know that's not the chemistry, right? The chemistry for a basic solution, you focus on the anion of the weak acid that would have come into it. Like weak acid means it wants protons. So where does it get those protons? Let's see. Oh, sorry, wrong one. From a weak acid. It gets those protons from water. It takes a proton from water, makes the weak acid, and it prefers to be over here and produces that. So the anion part of the molecule, if it's from a weak acid, that's the chemistry that gives you the basic. All right, let's see, 16. This one's starting to get too weak. If a solution is buffered at pH 9.5, pH 9.5 buffer, then the addition of a small amount of acid will cause the solution to have a pH of approximately, a small amount of acid will drive this toward the acidic side, but not very much. So a number that's close to 9.5 but less would be the one we're looking for. 7.5 is too far, 8.5 is too far, 10.5 is the wrong direction, 9.5. Solution will have a pH of approximately 9.5. Depends on how much acid you add. It'll be a little bit less than that, but that's the closest, the best answer is 9.5. Let's see, scroll. 20. Determine the concentration of an acid using an acid-base titration always involves completely reacting a measured volume of acid with a known volume of. Well, if you're going to determine the concentration of an acid, for simplicity's sake, let's say they're monoprotic and monobasic. So we're governed by the concentration of the acid times the volume of the acid equals the molarity of the base times the volume of the base. So which ones do we know? Concentration of an acid, this is unknown. With an acid-base titration, the volume of acid with a known volume, this is known, so this one has to be known with a known concentration of base. A base of a known concentration, that's required. Okay. Now, if you mix up, say monoprotic and dibasic or diprotic and monobasic, then instead of molarity, you have to use normality. But the concept is the same. That's an acid-base titration. Or the theory behind it. '24, in which of the following pairs of acids are both members of the pair strong acids? Oh, all right. Well, for A, nitric acid is strong, but nitrous acid is weak. So A doesn't work. How about B? Sulfuric acid and sulfurous acid. Right? The first one is strong, second one's weak. That one doesn't work. How about C? Hydrochloric acid and perchloric acid. Oh, yeah. They're both strong. In fact, perchloric acid is stronger than hydrochloric. Actually, they're both strong, but well, yeah. Chemically speaking, they're both strong because they completely dissociate in water. But hydrochloric acid, once it's dissociated, does certain types of reactions, whereas perchloric acid does other types of reactions that are more aggressive, actually. But they're both strong. So C is your answer. I've told you my perchloric acid story, right? Do you want to have some fun? You take concentrated perchloric acid, you take a nice big chunk of butter in a beaker, set it on your hot plate, and you fill the beaker with perchloric acid. And then you turn your heater on maximum, draw the sash, and evacuate the building. Because it will blow. Let's see, which of the following indicates an acidic solution? All right. A, B, and C, and then, let's see, this is 29. 29. A, B, and C. So A says pH 7.5. Nope, that's basic. And let's see, B, hydronium ion of 10 to the minus fifth. Oh, yeah. That's acidic. It's a lot less than 10 to the minus 7. How about C? Right. That one's acidic. And then OH minus concentration of 10 to the minus 8. That's acidic also, because this is much less than 10 to the minus 7. Okay, so these two are both acidic. That means two of the above. More than one, D. D is correct. And scroll. We're skipping a few. Oh, here we go, 37. One, two, and three. See which ones of these are true. Let's see. Both members of a Bronsted-Lowry conjugate acid-base pair must contain the element hydrogen. No. But if you have HCl and Cl minus, that's an acid-base pair. Right. You only have to find one example that doesn't fit the description, and you can claim falsehood. 2, the larger the value of the acid ionization constant for an acid, the weaker the acid. That's just the opposite. The acid ionization constant is, let's see, H plus minus, and H A. So the larger the value, the more hydrogen ions you have. That gives you the more acidic solution. So it should be the other way around. Or the larger the value, the stronger the acid. So this one's false. How about 3? Weak acids cannot completely neutralize strong bases. Yeah, they can. Yeah. Acetic acid and sodium hydroxide. You can completely neutralize the sodium hydroxide with acetic acid. No problem. Yeah, so that was false. All of them are false. Now, what's different is if you neutralize a strong base with a strong acid, you're going to get a neutral pH at equivalence. But if you neutralize a strong base with a weak acid, you're going to get a basic pH at the equivalence point. So when we titrate sodium hydroxide with acetic acid, we reach the equivalence point where hydrogen ions and hydroxyl ions are both equal at about a pH of 9.5 in that range. (38) 1, 2, and 3. Formation of a coordinate covalent bond is always part of a Bronsted-Lowry acid-base reaction. Formation of a coordinate covalent bond. If we have an acid-base reaction, acid-base. So we have HOH or H2O and BA. Now these are going to be, that's an ionic compound. This one has that positive and this negative. So where do the electrons come from for that bond? One side only. So that's true. Right? Acid-base, Bronsted-Lowry acid-base reaction is always a coordinate covalent bond formation. Yeah, one is true. 2, the compound H2CO3 is both a strong acid and a diprotic acid. Now, it is a diprotic, but it's not a strong acid. Carbonic acid is very weak. Right? Whenever you drink pop, you're washing H2CO3 down your gullet because of the carbonation. You dissolve CO2 in water, that's one of the products of the CO2. It combines with water and makes carbonic acid, but it's very weak. Right, so 2 is not strong. That's false. And 3, the pH of a solution with OH minus of 1 times 10 to the minus 8 is a pH of 6. Okay, simplest way here, what's the POH? POH is negative log. We can throw the 1 out because log of 1 is 0. Plus the log of 10 to the minus 8, negative log of 10 to the minus 8. Which is equal to 8. And then 14 equals pH plus POH. So pH is equal to 14 minus 8, which is equal to 6. That's true. 2 are true. That would be B. All right, 38. Oh, we got several in a row. 40. One, 2, and 3. All right, in an aqueous solution, Arrhenius acids undergo ionization and Arrhenius bases undergo dissociation. Yeah. Acids have a proton in there that has to ionize, because it's a covalent bond. And bases are ionic compounds that simply dissociate, right? So 1 is true. 2, production of the salt NaNO3 through a neutralization reaction involves the reaction of a weak acid with a strong base. That's false. Sodium hydroxide reacts with nitric acid. They're both strong. So 2 is false. And 3, the ion product constant for water at 24 has a numerical value of 1 times 10 to the minus 14. That is true. The ion product is what we call Kw, is equal to, that's an ion product, the cation times the anion. It's another word for it. So 2 are true. That's B. Forty-one. Oh, 1, 2, and 3. The 2 members of a Bronsted-Lowry conjugate acid-base pair will always differ from each other by one unit of charge. Yeah, that's true. Yeah. The conjugate base of the acid will have an increase in negative charge. If it's neutral, you'll have a negative. If it starts off negative, you have 2 negatives. But it leaves an electron behind when the hydrogen leaves. So yeah, it's always 1 unit of charge. That's true. Let's see. 2, an equivalent of an ion is the molar amount of that ion needed to supply 1 mole of positive or negative charge. Yeah, that's the definition of equivalent. How much of a substance, the molar substance, is required to deliver 1 mole of charge? And it's either positive or negative, doesn't matter. Yeah, okay. How about 3? In an acid-base titration, the indicator changes color when the reaction between it and the added acid is complete. Yeah, it changes color with tongue-in-cheek, because the color change occurs over a range of pH. But it centers on the balance between the acidic form or protonated form of the indicator and the non-protonated form of the indicator. Yeah, so 3 with qualifications is true. So we can say all 3 are true. Let's see. Oh, we got another one. 45. All right. All rainfall, even in unpolluted areas, is acidic. That's true. Why? Because when rain falls through the atmosphere, it picks up carbon dioxide and gives you carbonic acid. If I take distilled water, freshly distilled, and put it in a sealed container, it will be pretty close to pH 7. There's nothing but water in there. You leave it open to the atmosphere for several hours, and it will gradually go acidic every time. It's picking up CO2 from the air and convert it into carbonic acid. So if you need water that's pH 7, and you need to guarantee it's pH 7, you seal your container and you put a filter for any incoming air that replaces the air when you draw out solution. And the air has to go through something like sodium hydroxide pellets. And they will take that CO2 and suck it out of the air, so none of it gets in. Okay, so that one's true. Blood plasma, interstitial fluid, and intracellular fluid, three general types of body fluids, all contain electrolytes. That is true. Yeah, they all contain electrolytes, which is positive and negative ions. That's all that means. And three, blood plasma is slightly acidic because ions it contains undergo hydrolysis. No. Blood plasma is slightly basic, and it's buffered at a basic pH. It's a very narrow range. Remember from anatomy and physiology? Okay. Remember what the range is? I'll get you started. 3, 5 to 4, 5. Extremely narrow range. If it goes too far one way or the other, you're going to feel bad. Diabetics, right? They'll go this way a lot. And they will, I mean, if it goes far enough, long enough, they'll end up in a coma. Ketoacidosis, they call it. What your body is trying to do, since it doesn't use, this is particularly troublesome for type 1 diabetics, is your body's trying to use anything else it can for energy because it can't use glucose. So it uses other forms, and the product of those forms is acidic compounds. And they eventually exceed the buffer capacity of your body fluids. One of the products of that, if it's serious enough, is acetone. So if you've got someone who's in diabetic shock, all you have to do is just lean down and breathe and take in some of their breath. You'll smell acetone. Let's see. Oh, 49. I saw that on a comedy show. Remember who Danny Thomas was? No. Marlo Thomas, that girl? It's too old. Okay. Danny Thomas was a comedian and an actor. He had TV shows, variety show one time. And he did this short-lived comedy show on TV where he was a doctor. And the first episode, he was moving into his new offices and there was no furniture. So he had his receptionist get him a couple of boxes to sit on. And his first patient came in who was feeling really bad. And he sat him down on the box and they were close together. He leaned in and breathed. He says, "You go to the hospital." He smelled acetone on his breath. He says, "You're close to diabetic shock." Okay, 49. Sometimes TV shows and movies get it right. Sometimes they don't. Like Breaking Bad. I watched several episodes of that one and the chemistry was so bad. I said, yeah, I like Bryan Cranston. He's an excellent actor, but I said, I can't stand the errors in chemistry. Most of the audience won't know it. Select the response list comment. Best fits the description. Reacts with hydroniums to form HPO4 2-. So it reacts with this one to form HPO4 2-. Right? If this reacts with something to give that, this one's not going to pick up another hydrogen. It has to give it up. So we know this one's going to be the acid. That means we need the conjugate base of this one. That means what will accept a proton to make that? That one. So this is the base for the reaction. Gives you the conjugate acid. So PO4 3-, D, would be the correct answer. Everybody see how I did that? Okay. 54. Select from the response list for the acid that best fits the description, an acid that has more non-acidic hydrogens than acidic hydrogens. So the acidic hydrogens are the ones that are listed first. And the non-acidic ones are the other ones listed to the right in the rest of the molecule. So the first one, HCl, has more non-acidic than acidic. It doesn't have any non-acidics, right? So that one's false. How about HC2H3O2? Yeah, it has 3 non-acidic hydrogens and 1 acidic. Yeah, so that one's true. Oh, we found our answer. C is equal, right? And D only has 2 acidics and no non-acidics. So that answers the question. It has more non-acidic hydrogens than acidics. And 55. From this list, acid that best fits the description, an acid that completely dissociates in solution to produce negative ions with a charge of 1. -1 charge. Okay. Completely dissociates in solution. All right, so A, B, C, and D. HCl, what does it do in solution? It completely goes to, well, of course, hydronium ions, but that's the simplified version. This one, C2H3O2, this is acetic acid, C2H3O2. This one prefers that side. So it does produce some of this with a charge of 1, but it doesn't completely dissociate. So actually this one answers the question. But how about C? H2C3O2. All right, that's another weak acid. C3H2O2. This one is like acetic acid. It prefers this side. C3H2O2. H minus. It doesn't completely dissociate. How about this one? H2SO4. All right, this is a strong acid, and it's strong acid for 1 proton. So technically, this one does not completely dissociate because it only goes, it's only strong for 1. HSO4 minus. This one is weak. That one's strong. This is weak. So it doesn't completely dissociate. It only goes for 1 hydrogen. That technically is not a good question.
Say on the answer key,
Yeah.
the answers are A and G.
Oh, okay. So I took that into account. Either one would be correct. I must have encountered that problem before.
So I was looking at it, I was like, well, I wonder how this one's going to turn out.
How's he going to talk his way out of that one? Yeah. That's what I get for letting somebody else write my questions for me. Let's see, 56. Let's see. List the compound that best fits a salt whose dissociation product produces equal amounts of 2 ions. When we say equal amounts, we mean molar amounts. We're not talking about mass. Equal amounts. So equal amounts of 2 ions. KOH will completely dissociate. Oops. Boo-boo. That's true. That's a good one. Equal amounts of two ions. Select response. A salt whose dissociation. Oh, that's not a salt. That's a base. It's a trick question. This is a salt. And it completely dissociates into equal amounts of two ions. There you go. H3PO4 is an acid, it's not a salt. And D, K3PO4 doesn't produce equal amounts. 3 Ks plus 1 PO4. Okay. Yeah, that's kind of tricky. Got to read the whole question. How about, we're going to skip a few. A lot. Must be a lot of repetition there. 71. Need to work a problem for this one. Math problem, it looks like. '71. Okay. What's the pH of a buffer that is 0.25 in a weak acid? So a weak acid, the concentration is 0.25 molar. And the conjugate base is 0.260. Conjugate base is 0.260 molar. And the pKa is 5.53. You remember what to use for this one? Anderson-Hasselbalch. pH equals pKa plus the log of A minus conjugate base over the acid. Okay. So fill in the numbers. Plus the log of, let's see, base on top, 260 and to 0.250. Get my calculator out. So let's do this one first. 0.26 divided by 0.25 is 1.04, and then take the log of it. Log. So that's 1.703 times 10 to the minus 2. And that's plus this value. That's equal to, let's see, two significant figures. 5.55. C. Didn't change very much, did it? Okay. Well, that's it.